Have a session now exploring opportunities in using AI and LLM with CI. And as our first speaker, I'm going to welcome Jingun. Thank you so much. Who's coming from SAP to us.
Yeah.
And I want to give him a warm applause. So nice to have you.
Thank you so much. So today's talk is about the hidden costs and challenges in evaluating automated CI repair, especially in SAP HANA. So last year, we had a university research collaboration with the students and professors from KAIST and Korea University. So this talk is more about the stories from our side, like a company side, who actually had to provide an evaluation harness and some environment. So I will not cover the fault localization or program repair approaches in detail in this session, but I will cover more about the challenges we have and some limitations. So because Eva already covered the SAP HANA very well, so I'm not going to repeat this again, but I wanted to highlight that SAP HANA is an in-memory database, which requires some memory space, of course, even for testing. And also it has a huge code base. And also, and it's written in C++. It's actually one of the challenging programming languages for large language models. This is a brief overview of how the testing is done in SAP for SAP HANA. So in the pre-summit testing, in the left side, we have a smaller scope and less execution time, but more frequently. So we can, of course, developers do some local testing on their machine, like running unit tests and so on. And also each team, the component development team, they have their own subtopic branch. And whenever they push their code in their subtopic branch, there is some CI runs. But of course, the test pool is smaller than the other the testing. And then when some features or bug fixes are ready, they push it a set of commits to the main branch. And then the larger set of testing is triggered and also reviewed. So in this session, we will focus more on mostly on the pre-summit testing part. And this CI failure fix is also targeted to the pre-summit failures. I want to briefly also introduce our prior work. In 2024, we wanted to use the large language model to fix our problems in SAP HANA. So we thought that fixing the compiler warnings was the easiest problem we can tackle first. So using some output from the language server by providing those contexts, we were able to generate the proper compiler warning fixes. And as you see here, like more than 90% acceptance rate was, it seemed very promising. So as a next step, we also wanted to try this fixing CI failure last year. So we thought that in compiler warnings, the failure signals are very precise. So it doesn't even require fault localization because we know where the problem is precisely. And also we thought that maybe the CI failure, we have a more or less precise failure signal because if task fails, we know where the task has some issues. And also we know which source files are changing. So we have a very limited search spaces, that's all. And also in compiler warnings, the fixes are very localized. So we don't have to fix the files like in different component or something. And also we thought that the CI failure, we thought the fixes can be localized also. And the evaluation was very important, but in compiler learning, we can directly get this evaluation from the compiler with not much effort. And also we thought that this CI failure, we can just rerun the task again, so that we can see if the failure is fixed or not. So our plan was we used the Closed Code from the famous AI coding agent and the Closed Sonnet 4.5, the latest model back then, and the HANA code base. We gave these the HANA code base with the version that had a CI failure, and also some CI failure info like test logs or some other related some test artifacts and so on. And then we faced some challenges we didn't expect initially. First one is curating a ground truth data set, and secondly, providing a useful context to LLM agents, and lastly, evaluating patches having this test like this. So let me cover one by one. So first challenge was curating a ground truth data set. To know that if our agent-based CI repair is good or not, we need some kind of a ground truth data set. Maybe you're familiar with the SWE bench or some benchmark data set where you can run the agent and then see whether the agent fix the problem or not. So with the same approach, we also wanted to collect this collect and build this kind of a data set, ground truth data set for the evaluation of the patch generation. This is kind of summary. I will cover these in more details, but as a kind of summary, we had some problem with the mislabel failures. Some failures are assessed wrongly, maybe the false positive or negative. So, and also if developer fix the test files also, then it's kind of a moving target. So it's hard to expect the LLM agent also to fix the test files. So it's one of the challenges we also observe. And also some test failures are just abandoned well, if it is like GitHub, if a pull request is rejected, then maybe I should.
Yeah.
Yeah, let me use this microphone.
Yeah, right.
Okay. So some developers just preferred abandoning this pull request or Gary change and then started a fresh pull request or Gary change. And also sometimes rebase itself fix some test failures, so it can be a kind of a noise in the data set. Firstly, the incorrect failure assessment. Now we have two different branch categories. First one is master, and the second is subtopic. Master is one of our main branch, and subtopic branch is the category of the branch. So there is no branch that's named a subtopic, but it's more like all different branches of the components. So in master branch, whenever there is a CI failure, there is a dedicated colleagues who are actually assessing those failures using automated bot, and even they review it manually. So those results are, how to say, is very well categorized. So even if it, so these counts is the merge change. So merge change with the error state means it can be either flakiness or it's kind of a known issue. So human reviewer regarding this test failure is a known issue, and if the bug is being tracked somewhere, then they just merge the changes because the change itself is not responsible of the problem. So we can kind of trust this assessment result from the master branch. But the problem in the subtopic branch is that there are no dedicated team for the review. Also, because the developers are owning that subtopic branch assessment, and also they know a lot of this component and everything. So sometimes they just ignore some test failures, and maybe they just postpone the fixes in later comment. So they have more freedom. So it's very hard to trust these assessment result in the subtopic branches. But the challenge here is that usually subtopic changes are better repair targets because they are just small comments, and each comment has some dedicated purpose. But when they push it to the master branch, for example, like as a pull request or getting change, then many comments are merged together, and sometimes will feature A or bug fix B. It can be merged in the same change, or some refactoring can be even included as well. Because testing in the master branch can be a bit expensive, so having very fine-grained changes in this main branch is a bit costly. So although master branches are more, I would say, more reliable, having more reliable assessment result, but it's too coarse-grained as a repair target. So in our research project, we use only the master branch's assessment result because we couldn't really use these subtopic branches assessment result. But then we are now losing many of the meaningful repair targets, which is a bit of a shame. And another challenge we had was that among these patch sets in our data set, many of the fixed patch set contain the test file changes. So as you see this, more than 80% of the changes contain the modification in the test-related code. It is not just about exactly the test that failed in the CI, but all these files that are related to the test. So it can be like XML file that is related to the test configuration or something like that. So when we ask LLM to fix a CI failure, it's hard to expect that LLM fix some problem in the source code and the test code at the same time. Because if we if you allow agent to change the test evaluation, then it can just remove for example, like assertion statement to just make the test pass. That's all. So this is too, I'll say, challenging to open up that kind of possibility. So now we chose to only use this 80% of the data set, and we had actually people look because we know that in many fixed changes, there are many, in general, test files were touched. But then is it like failed test cases or different test-related files? Interestingly, only the 15% of the cases touched the actually failed test cases. So in 85% cases, although it was test related, but it changes some different test cases or test related source code. So this also makes the analysis a bit difficult, because if it is just fixing the failed test cases, then maybe we can, for example, use the fixed test case as an evaluation test case. But now we see this like having some modification, not only in the failing test, but the other test-related code. It's hard to have them in our data set. Yeah, that's kind of a summary. So 82% of the fixed patch set also modified the test files. And yeah, that made evaluation a bit more difficult. So we excluded this 82% of the fixed patch set. So now our evaluation data set became really small because we discarded a lot of the majority of the fixed patches. And also some noises from rebases. Maybe this is not the major problem, but still, when a patch set A was created, the head could be parent C, and there are some changes files. And then when fixed patch set B was pushed, the parent can be updated, like parent B. And if we just leave the patch set A and B, then there can be a lot of file changes from the rebase and so on. So we took only the intersections, but this heuristic may miss some possible some relevant changes, but that was the approach we could take. And then so the second challenge was what is the meaningful context for LLM agent, especially in database testing. So, for example, if an LLM agent requires a full row test logs, then because persisting a huge test artifact can be costly, so we need to decide whether we need to know if this is meaningful to keep and so on. So we wanted to know which context is meaningful and effective for LLM agents. And firstly, in SAP HANA's integration testing, we use the Python and SQL queries to interact with the live. Sorry, let me see. Sorry. I don't know what it was. Let me continue. Okay. Okay. Sorry. And okay, I forgot what I was doing. Right. So firstly, we wanted to know if a test code is meaningful for the fixed generation. But because the HANA HANA core is written in C++, but the test code is Python and SQL script. So we wanted to know if this testing code is meaningful for agent to generate a proper fix. But when we tested, even when we added the test code, it didn't really provide a better root cause analysis. So because we think that this because we are using it's a different programming language, and also even trace in trace messages that it also contains a part of the test code. So I think the test code itself does not really provide additional meaningful information. But when we provided the bug inducing comment, it actually enhanced the fault localization result a lot. So for the once the localization, which means just without multiple interaction with the agent, fault localization and also the repair touched ground truth actually fixed files. So more with the bug inducing comment. And of course, if we provide the bug inducing comments, then and it also reduced the search space a lot. So in average, bug inducing comment had 28 changes files, although it's not small, but that could that help the agent to understand the CI failure better. And also, we wanted to know if we have to provide a reverse row test failure logs, because in database testing, the logs are actually printing out all these detailed information, and sometimes we may think that these kind of detailed information can be a clue for the debugging, but when we tested, providing the row a log was not really helpful to generate the plausible patches, but had even worse performance, and it was even more expensive in more token usage and so on. So when we compare with the between minimized traces and minimized and plus full logs, the minimized traces showed a better repair result, and also showed cheaper cost. And the last challenge that I want to share is that because in database testing, flakiness is quite very common, because especially in integration testing, we cannot expect the deterministic behavior in a database when we send some kind of query. So this whenever we generate the patches, we have to also make sure that if it's a flaky test result or not. But even before that, among the 122 candidate patch set, when we try to reproduce the CI failure, actually we only around 80% was successful. So which means that some rejected changes with CI failures were rejected because of the flakiness or some other issues. So even this reproduction was not 100% I'll say available. So and even with that, we had to also make sure that if a test failure is from the flakiness or not. So for our evaluation of this patch, the CI repair, we whenever there was a test failure, we had to rerun 3 additional times on separate machines. But if you imagine this, we have to download the binaries and install it, and then execute the workload on the 3 different machines at the same time. Then it's actually very costly. So to verify one generated patch, it required it took more than an hour or so. So it was we found this too expensive. And also, even if a test was successful in the first run, but we are not sure if it is success from the flakiness or not. So for example, or even if we rerun like 3 times, but we don't know if it will be successful like a 4th or 5th run. So that also make this evaluation a bit more challenging. So when you look at some benchmark performance results from the different agents, they usually provide a pass and K metrics. But I think this that kind of metric doesn't consider this non-deterministic test results. So I think that especially for this kind of I'll say for example, like this kind of a database testing where the non-determinism is quite prevalent. we have to consider this non-deterministic test result in the evaluation. Okay, so as a summary, I introduced the three main challenges we had when we try to apply the agent-based CI repair. First challenging that I showed was the ground truth curation, because many of the fixed changes contain the test files changed also, and some failures were mislabeled and so on. And the context for LLM agents, we observed that bug-inducing commit was very meaningful, the entry point for the deeper debugging, and also making this the test load in a more efficient, making this test load more concise and minimal was helpful for better repair. And also, we have to also consider the flakiness in evaluation. From this flakiness, 17% of the cases were not fully reproducible, even in our filtered data set. And also we have to rerun the fail test for the flakiness examination. So for this, we have to consider this kind of a resource cost for flakiness detection in evaluation. All right, so this is the end of my presentation. Thank you so much. And if you have any questions,
thank you. So, is that working? Yeah. Thank you so much, Jingun, for your presentation. Looking at the clock, I feel like we have 2 minutes for questions. Let's get a question.
How do you prevent the negative impact of introducing the bug, introducing commit for program repair in flake tests? You know what I mean? Like you have a flake test, you evaluate some bug introducing commit. That seems to be possibly, it may have spurious negative data that can actually impact the repair negatively.
Okay, so if this bug-inducing commit causes some flakiness in test result, then it makes even more difficult to debug, you mean? Okay. Yeah, then actually I haven't really thought of, but yeah, actually that's a really good point. Yeah, unfortunately, we haven't really analyzed the flakiness that was caused by the source code changes deeply, but we just wanted to know the if the generate patches have any kinds of flakiness in the test behavior. So, but yeah, I think that's also very interesting point. Yeah, thank you.
All right, thank you. Any further questions?
I thought we were doing this.
Oh, yeah.
Well, otherwise, I have lots of questions.
Yeah, let's
But it was
do
a great
those
presentation.
in a coffee break. Yes. Thank you so much.
Thank you.